everybody, welcome back to another Gregorius Maths video. Today we're going to be taking a break from algebraic topology and we're going to be looking at some algebra. Okay? So, today we're going to be looking at exact sequences, normal subgroups and quotient groups. Okay? So first of all, H, a subgroup of G, is normal. I forgot how to write that H is normal. I forgot how to write that H is a subgroup of G. So I'm just going to use subset notation for now. Is normal if for all G in G, G times H times G inverse is equal to H. Okay? Now, we'll see that this can be the kernel of a homomorphism. If we have G prime is the set of cosets of H, okay, then we can define a product, okay? This is going to be a group, okay? Why? Why, I ask? Well, XH times YH is defined to be XYH. Okay? You can verify yourself that this is associative. That's very easy to verify. Okay? XH times EH, where E is just the identity, is equal to XEH is equal to XH. Okay, so EH is the identity, or just H is the identity. Okay, because this is the same as saying H. It's just easier to see when you write EH, okay? And inverses are defined as XH, the inverse is X inverse H. Okay, very easy stuff to define, okay? Okay, so we do see that G prime is a group. Now, let F be a homomorphism. Okay, it takes you from G to G prime. Okay, and it's defined as f of x equals xh. Okay. Now, now of course the subgroup H is going to be contained in the kernel, but actually it turns out that H is the kernel. If f of x equals h, okay, since H contains the unit element, this means that I'm sorry for being trash. Okay, implies that XH equals H, and since H contains the unit element, that means that H is the kernel of F. Okay? Now, what we actually constructed here is called a quotient group. So, G prime is equal to G mod H, the set of cosets of H, okay? And the map F was the canonical map, okay? So now, before I move on to exact sequences, allow me to make a quick remark about normal subgroups, okay? If we have H sub I, okay, indexed by some larger set I, being normal subgroups of G, for example. This implies that the intersection over all I and I of H sub I is normal. In G. Okay, why is that? Well, because for all x in G, okay, x times one of these h sub i's times x inverse is going to be h sub I. But if all of these h sub i's have this property, that means that no matter what their intersection is, that subgroup we end up with will also have that property. Okay? Now, we introduce exact sequences. Okay, what is an exact sequence? 2, 4, 6, 8, is that exact? Because you add 2 every time, does that mean it's... What? What it means for a sequence to be exact is let G, which maps onto H, which maps onto J, for example, via G, be a sequence of homomorphisms. This is exact if the image of F is equal to the kernel of G. More generally, if we have G sub 1, which maps via F sub 0 to G sub 2, which maps via F sub 1 to G sub 3, which maps so on, so on, so on, all the way up until G sub n minus 1, mapping via F sub n minus 2 to G sub n. Yeah, okay. Then for I going from 1 all the way up until n, this is exact if okay, the image of F sub I the image of F sub I minus 3 is equal to the kernel of F sub I minus 2. Okay, basically it's exact at every point. So here it's exact, this little bit is exact, this little bit is exact, this little, so on, so on, so on, then the whole thing is exact. Now, without knowing it, we constructed our own little exact sequence. Okay? If we have H mapping onto G via the inclusion map, and that maps onto G mod H via the canonical map, okay, this is exact. Okay? Okay? Now, if we look a little bit more, not just three homomorphisms, okay? So we have 0, the trivial group, okay, which maps onto G prime, which maps via F onto G, which maps via G onto G double prime, okay? This being exact has some nice consequences. We can deduce some things about these groups, okay? If this is exact, okay, then, well, that says that F, that means that the image of F equals the kernel of G, okay? But if the image of F is the kernel of G, that means that F is injective, okay? Also, if the image of F is the kernel of G, that means that the kernel of G is surjective. Okay? I can write surjective. Alright? So immediately we can deduce these things about these groups, which we wouldn't be able to without knowing that these are exact sequences. Okay? So now if we set H equal to the kernel of G, this is the exact same thing. So let me rewrite it again. Okay, so the vertical rows are isomorphisms. Okay, so the trivial group is of course isomorphic to itself. Okay, now this thing here is exact. Sorry. Okay, and the vertical rows are isomorphisms. Now, this map is commutative. This diagram, sorry, don't know why I'm calling it a map, is commutative. Okay? So this is really cool, okay? But it's about to get better, okay? Whoop! So we look at induced homomorphisms. What is an induced homomorphism? So let F from G to G prime be just a normal homomorphism. Okay? Now with kernel. Okay? And now let phi be the canonical map, which takes you from G to G mod H. Okay? Okay? Now, we say that F star isn't... I claim that there is a unique map, F star, okay? Okay, unique. F star, which takes you from G mod H into G prime. Such that F star compose phi is equal to F. There exists unique F star from G mod H to G prime such that F star compose phi, sorry, is F, and F star is injective. Okay? Now how should we define this F star? Well, if f of xy equals f of x for y in H, okay, so we'll define F star of xh equal to f of x. Okay? Now you can verify yourself that this is a homomorphism. Okay? And it gets even better because this induces an isomorphism. An isomorphism. Lambda, okay? Okay? Such that, lambda which takes you from G mod H into the image of F. Okay, now this can be factored into a succession of homomorphisms the following way. First we have G, which maps via the canonical map phi to G mod H. Now using our induced isomorphism lambda, we can map it onto the image of F, and via the inclusion we map onto G prime. And with this cool ending, I find this so cool.